So through this video, we're going to talk about exponential functions. And what that means is that we are going to be dealing with graphs that have equations that have exponents, simply put. And you'll see through these graphs that the rate of change will grow exponentially. So the rate of change will get bigger and bigger and bigger, or smaller and smaller and smaller as time goes on. So as we take a look, it says exponential functions. An exponential function of the form y equals a times b to the x, where a does not equal 0, b is greater than 0, and b does not equal 1. Let's talk about why a cannot equal 0. So a cannot equal 0 because, for example, if a did equal 0 and I had y equals 0 times b to the x, well, anything times 0 just gives you y equals 0. So that's not going to help us. So a cannot equal 0. Now, we talk about where b is greater than 0. So your b has to be greater than 0. Your b cannot be a negative number. And here, b has to be greater than 0, but is also not allowed to equal 1. So it can be any number greater than 0, but it's not allowed to equal 1 because, again, let's think about it. If I have y equals, I'm just going to even leave the a in here, a times 1 to the x, no matter what you put in for that x, 1 to any power is still just going to be 1. So that doesn't help our cause to grow exponentially. Okay, let's continue on. And you can see down here a couple of these graphs that are growing exponentially. And notice, as time goes on, they're growing bigger and bigger. Here, we have y equals 2 to the x. And then notice it's going as x is getting bigger, the y is getting bigger. So, and this is a positive 2 to the x. Here in the bottom, we have a downward slope. And we have y equals negative 2 to the x. And notice, as my y values are getting bigger, or my x values are getting bigger, my y values are getting smaller. Okay? All right, I wanted to talk about linear functions versus exponential functions. If we take a look at the linear functions, we know that this table is linear because we can see that here it's going up by 2, up by 2, up by 2, and our x value is going up by 1, up by 1, up by 1. So here my rate of change is going to be 2 over 1. Now notice with linear functions, the rate of change is going to be either added or it could be negative, right? So here we're going up over 2, we're going up 2 over 1 every time. We also could go down, right? So add or subtracted. Okay, we know that this is a linear equation because you have a y and an x, and we have this constant rate of change. As we take a look at the exponential function table, here we do have a constant rate of change. Notice every time it's being multiplied by 3. But because you're multiplying by 3, like you're multiplying each previous number by 3, that the space, the gap in between these numbers, get bigger and bigger. And here we're going up by 1. So yes, we still have a constant rate of change, but here notice that we're multiplying. So if you notice that your table is going up through multiplication or division, that's a good way to tell. Okay, so here our rate of change is technically multiplying by 3 over 1. As we look at our table, you'll notice you have y equals 3 to the x. You have an exponent here. Anytime that you have an exponent, you know you're going to have an exponential function, whereas anytime that you do not have an exponent, you're going to have a linear function. Okay. Suppose 30 flower beetles are left undisturbed in a warehouse bin. The beetle population doubles each week, and the function of f of x equals 30 times 2 to the x gives a population after so many weeks. I wanted to show you a couple things that they don't talk about yet, but they're going to, is this function right here. So we know an exponential function is y equals a times b to the x power. They don't talk about it yet, but I'm gonna tell you that your a is always going to be your initial value, and the b is going to be your rate of change, and the x is going to be over the period of time, right? So here we have f times f of x equals 30, because that's how many we started out with, times 2 to the x. Now we get that 2 because here it says that it doubles each week. Okay. And also I want you to notice that they talk about week here. One of the main things to really pay attention to when we're doing this is what measurement they're giving it to you in, because here they say it doubles each week, but they give you the length of time in days. So 56 days is equal to 8 weeks. So the x, the amount of time that you're putting in for the exponent, is going to be 8, because again they want the answer in weeks. So we get f of x equals 30 times 2 to the 8th, 30 times 256, which gives you 7,680, okay, beetles. So after 56 days or 8 weeks, there will be 7,680 beetles. Okay. Erase this real quick, and let's look at the bottom one. So, the bottom says an initial population of 20 rabbits triples every half year. The function of f of x equals 20 times 3 to the x. Let's talk about where those numbers came from. So, they give us the function for us. So f of x equals 20 times 3 to the x. Well, we said that the a value, or here is 20, that is our initial, okay? Then it triples, which gives us our 3. That's our rate of change. It triples every half year. So half year, that means you're getting 2 times a year over a period of 3 years. So 2 times a year times 3 years is going to give us 6. So our x value is going to be 6. So for a function 3 to the 6 is 729. So we get grand total of 14,580 rabbits after 3 years. All right, let's have fun. So here they're just asking you to graph. So they give you a function of y equals 3 times 2 to the x, and they give you a set of x values, very typical, -2, -1, 0, 1, 2. And then they put them in the function to give you an output or a set of points. You plot the points. Notice it's a smooth curve, and the distance between these curves gets bigger and bigger every time. Okay, so let's go ahead and we are going to put together a table for the first one. So y equals 0.5 times 3 to the x. X, y. All right, so we put together a table here, and I have a set of values. So we're going to go ahead and graph them. So -2, 0.056. That's going to be a nightmare. So we're just going to put that at 0. So here, and then -1.167. I don't know, we're going to say that's here. And then 0 and 0.5. And then 1 and 1.5. And then 2 and 4.5. So you can see from here, our graph's kind of going to go like this. All right, let's take a look at the next one. And here they changed it and gave us a -0.05. So y equals -0.5 times 3 to the x. So -2, -1, 0, 1, 2. And we'll see what that gives us. All right, so we're going to go ahead and graph these. And you'll notice I have the same exact y values as the other, except for these are all negative. So what do you think is going to happen? I'm going to graph this one right here. And then this one right here. And 0.5. All right. So as we look at these two graphs, you'll notice that they are exact opposites of each other. One is going up while the other is going down. So they are a direct reflection of each other. One is going up, which is this positive one, and the other is going down. Okay. As we take a look here, they give you an equation to solving one variable equations. And you'll see that they gave you an equation that looks like the one above. Now, the trick to this is not really a trick, it's the directions, is when you go to graph this, you are going to graph this as two separate functions. You're going to have one side of the equation is going to become 1, and then the other side of the equation becomes the other. So if you're in your graphing calculator, if you use Desmos, whichever one that you use, you would do y equals 2 to the x, and then graph y equals 0.5x plus 2. And when you get those, what you're looking for, where the lines cross, those are going to be your solutions. So for this, you have a solution of negative 3.86 and then 1.5. We're going to take a look at these bottom ones. So in the bottom, so for the first one, you have 0.3 to the x equals 5. So what I did was I used Desmos, and the blue line is y equals 5, and the red line is y equals 0.3 to the x power. Okay? Where they intersect, that is going to be our solution. So here, our solution is going to be negative 1.5 and 5. Okay, let's take a look at the next one. Now as we look at the second graph, when I graph this, the green line was y equals negative 2x. The red line was y equals 1.25 to the x power. Here we have one solution, which is negative 0.52. Again, all you're looking for is where these two lines intersect, but the key is when you graph these is to separate them into two different functions. For letter C, the black line, that is y equals 3 to the 4th x minus 4. And the purple line, is going to be y equals negative 2 to the x power. You have your intersecting point, and that's what we're looking for. Take a look at the next slide. All right, so I'm going to go through a couple of these to just review with you and to make sure that we really understand what exactly it is that we are going over. So for number 8, it says, tell us whether the rule represents a linear or exponential function. Explain why or why not. In number 8, we can see that here 2 to 8 we multiplied by 4. From 8 to 32 we multiplied by 4. From 32 to 128 we multiplied by 4. So because we're multiplying every time, that's going to give me an exponential. Whereas if I look at 9, notice my rate of change is I'm adding 3 every time. So because this time I'm adding 3, this is going to be linear. Going through 10 through 13, again, we're looking for that exponent. So if you have an exponent, you know it's going to be exponential. Here, exponential, 11. No, there is no exponent, so this is going to be linear. 12, you have an exponent, so that's going to be exponential. And 13, all linear. 14 through 17, they're asking you to plug in the value that they give you for x. So here you would get f of x equals 6 squared, and then f of x equals 36. And you would do that for each of these. You would plug in the value that they give you for each one. All right, so I've added the answers here if you want to go ahead and check those. Again, all you were doing was plugging in the value that they gave you for the exponent and then doing the math. I want you to take a look at a couple of these word problems and help set those up. Again, remember, at least for here, they're giving you the equation. I do want to remind you, though, that the equation is y equals a times b to the x, where a is going to be your initial value, and b is going to be that rate of change, and x is typically the amount of time that something is going on. But again, when we're trying to figure out what we're going to use as the exponent, you really need to pay attention to how they're breaking down that time. So here they said an investment of $5,000, so that's our initial value. And that initial value doubles every decade. So they gave us the initial equation. The initial equation, 5x equals 5,000, because that's our initial value. That's what we started with, times 2, because they said it doubles, and then to the x power. Now, here comes the important part. What are we going to use as our exponent? Notice they said every decade, so every 10 years over a period of 30 years. So what's 30 divided by 10? Because it's 30 years. And then we have to divide it by 10 because 10 years is in a decade. So that gives me 3 decades. So I'm going to plug a 3 in for x. So what does that mean? We get an answer of f of x equals 40,000. So what that means is after 30 years or 3 decades, the investment will be worth $40,000. Okay, so next one we have, it says a population of 75 foxes live in a wildlife preserve, quadruples in size every 15 years. The function, so again here, they gave us the function of y equals 75 times 4x, which makes sense because it said our initial value is 75 foxes and it quadruples, meaning 4 times, every 15 years. So we have to keep that 15 years in mind, and they're asking for it over a 45-year period. So it's 45 years, but they're saying that this occurs every 15, so we're going to divide that number by 15 years. So the exponent is going to be 3 because it happens 3 times over a period of 45 years. I'm going to erase this real quick. That's not exponent. So we're going to go ahead and plug in this 3. So I get y equals 75 times 4 to the third. So y equals 75 times 4 is 16 times 4. So I get 64 times 75. So I get y equals 4,800. So what does that 4,800 represent? That represents how many foxes there will be after a 45-year period. So there will be 4,800 foxes after 45 years. And you know I'm a stickler for writing answers in complete sentences. Okay. So here, what they're asking us to do is they want to know the solutions to each of these equations. So what I went ahead and did, I'm going to make that one smaller. Now, remember we talked about at the beginning of this that you're going to take each equation and graph them separately. So I'm going to put the first one in. So the first one I'm going to put in as y equals 4 to the x power. That's going to be that red line. Actually, I'm going to change the color of that. Okay, now it matches. Done. Okay. And then I'm going to graph the second line separately. So that's going to be y equals 3/2 x plus 5. So you'll see here that it actually gives us 2. It gives us 2 solutions. So that would be your answer for the first one. Okay. Again, notice here they give us 2 solutions, one for this point and the other for this point. So when you go to graph these, you do have to put them as separate equations. Let's look at the second one. So now let's come over here. Again, I'm going to take the one on the left, graph that first. And that's going to be y equals x plus 3. And then I'm going to graph the second one, y equals 3 to the x power. Again, this gives us 2. This gives us 2 solutions. One there, one there. And those would be your answers. So yours is going to be a little different because you're going to be doing it in a calculator. But I mean, if you can use Desmos to check your answers, then I would. Why not? If you have any questions, you can go ahead and let me know. But this should really cover that introduction to exponential functions.